Okay. Yeah, so the first thing we'll talk about today, since this is the introductory lecture, is a very simple question that what is the subject of physics really? Okay. If we were to explain in just a few, maybe one or two sentences to a lay person, a person not of science background or person who's not necessarily preparing for any science-based exam, but just a curious person, that what is this subject physics all about? Okay. Can any of you give me an answer? Can you explain to me? Yes, uh, Parv has answered that it is the study of our surroundings. Okay.
Can we say it is the
Study
study of
of
our
laws
physical
of
world?
nature.
Sorry, come again. Can you just speak a little bit louder?
Laws of nature.
It is the study of nature. Okay. So I have a couple of answers here. It is the study of surroundings. It is the study of nature.
Uh,
Yeah,
it
tell me.
explains why something around us happens.
It is a study about why things around us happen. Okay, I have some very
And
good
how they
answers.
occur.
Okay, so
So it's also the study of how things work.
how things work. Okay, very nice. So I have some more specific answers in the chat message also. Now, like for example, I have a very interesting message by Anandita. Okay, it says it is a mathematical approach towards science behind why a certain thing happens. So now I will start adding some keywords. Okay, so mathematical approach to science and why things happen. Okay. Also, number of people have said that it is to do with physical events. Okay. For example, Shaurya has said that it is the study of physical occurrences. Sai has mentioned it is the analysis of the surroundings. Okay. Misha has answered that it is the study of energy and matter. Shubham has answered that it is the study of physical things in the universe. Okay. Somebody else has answered that it is the study about the behavior of things. Okay, so we have got a lot of keywords like this. It is about physical occurrences. Somebody else has said it is about energy and matter. It is about how things behave. Okay. So these are all, through these keywords, we can understand more about what the subject of physics is. Okay. Now, if I start looking at some of the keywords here, for example, nature, or if I talk about physical occurrences, okay, we can narrow this down a little bit more. Okay, for example, what is nature itself? Okay, it is everything that happens in the natural environment around us. So, for example, that includes biological processes, it includes physical processes, okay, etc. So, how do we separate, for example, what we study of nature under biology versus what we study of nature under physics? Okay, or is it that physics includes everything, including what we study in biology? So, through that, next we come to this term, physical occurrences. Okay. So to bring this in perspective, I will just use another term. Okay, that physics is the study of all physical phenomena. Now, occurrence is the same thing as phenomena. Okay. So it is a study of all physical phenomena. Okay. But then what is the range of physics? Is it about the physical phenomena in our lives, or is it about the physical phenomena on Earth, okay, or in the world around us? So the range of physics, as you know, is the entire universe. Okay. So it is a study of all physical phenomena in the universe. Okay, that is the entire range of the subject of physics. So this I can say, from the conclusion of all these keywords, I can say this is like a small single line explanation of what we do in the subject of physics, or what we study in the subject of physics. Okay. So from that, first thing we'll want to know is, what do we mean by the term physical phenomena? Can somebody explain this? You can explain with an example also. What do we mean by the term physical phenomena?
Something that we can see.
Something that we can see, okay, that means it should be visible. But is that necessarily true? For example,
Yes.
what is happening inside an atom, right? Is it not a physical phenomena?
So, but we can see that. It's just that we need better eyes.
Yeah, in that sense, you can say you need an electron microscope, or you
Yeah,
need some kind of,
you just
yeah,
need a microscope. Yeah, but we can see that.
okay. But suppose there is something that we are not able to see, for whatever reason, like, there might be a galaxy that is like a few billion light years away, right? And the light from that galaxy, what is happening right now, will only reach us a billion years later, right?
Yes.
So we can't see really what is happening, but in that sense, in the traditional sense of the word see. Okay, yeah. So I mean, it's okay. We can say physical phenomena should be visible or something, but can we have a more technical definition of what we mean by physical phenomenon?
So
So
like
firstly, what does the
physical
term phenomena mean? Okay, sorry, I'll come back to that. What does the term phenomenon mean? Phenomena is the plural for phenomenon. Okay. What is a phenomenon? It is just a simple event or occurrence. So any event or occurrence is called a phenomena. Okay. And the plural of a single phenomenon is phenomena. Okay. Yeah. Somebody was saying something. What more technical definition of what is the meaning of the term physical?
So like physical phenomena can be like something which is affecting the other things in a system. Like when we are throwing a ball, there is somebody catching it. So
Very good.
there's an action there. In a galaxy,
Right.
like there is gravity affecting the other planets, other system, like other whole universes. So we can identify it as a physical phenomenon.
Very nice. So now we are coming closer to the explanation. Okay. So what we are saying is that a physical phenomena is one where different quantities affect each other. So one of the examples you took is when we have what we call motion under gravity. Later we will study it as something called projectile motion. When we throw something on the surface of the earth, it is the gravity of the earth's mass which is affecting its motion primarily. So when we say things that affect each other, for example, in the case of the object moving under the action of gravity, what are these quantities we are talking about? It might be displacement in terms of time, that after how much time the object has had made how much displacement, or it can be the distance covered by an object. Now you know that distance and displacement are different things. It can be velocity, can be kinetic energy, it can be linear momentum, right? So it can be acceleration, though in the case of something moving under gravity on the Earth's surface, the acceleration is uniform. Anyhow, so we are talking about quantities which affect each other. So more specifically, what type of quantities do we talk about in a physical phenomena? So any phenomena or event will involve different quantities affecting each other. Now, for example, if I talk about something very abstract, instead of a physical phenomena, I talk about an emotional phenomena. So there might be quantities which affect each other in terms of your emotional understanding of things. You might have read something which is conveying a certain sentiment, which is written in a certain language. So that is appealing to your vocabulary, and through your vocabulary, it is creating a emotion in your mind and all that. So there are quantities involved over there also, but are they involving physical phenomena? No, because in physical phenomena, the things that are affecting each other, okay, these things are called quantities. What type of things affect each other? It is physical quantities. So physical phenomena, it is a phenomena in which, or they are phenomena in which physical quantities affect each other. So it has to be a little bit more specific, that it is about physical quantities that affect each other. And now we have a better definition, that what is a physical quantity? I'm sure all of you know this definition. Anybody can give the answer specifically?
Anything that has matter and can be measured.
Yes, anything that can be measured. Okay, anything that can be measured specifically is called a physical quantity. So these are quantities which can be measured. Okay.
तो होने का है तो होएगा.
Sorry, come again, beta.
No, sir, I accidentally turned on my mic.
Okay. So now we are getting to a more sort of specific explanation, that physics is the study of all physical phenomena in the universe. Okay, and by physical phenomena we mean events or occurrences in which physical quantities are affecting each other. So for example, if we are talking about motion under gravity, it is gravity, okay, velocity, time, displacement. These are all the various kinetic energy, momentum, etc. Gravitational potential energy, you can say. These are some of the physical quantities which are measurable, which are affecting each other during that particular motion. Okay. If we are talking about, let us say, the motion of a planet around a star, like the orbital motion of the Earth around the sun, then again it is how the momentum of the Earth is affected by the gravitational pull of the sun. The gravitational pull between the Earth and the sun is affected by the individual mass of the sun and the Earth. Right? The sun is many billions of times in mass compared to the mass of the Earth. So the gravitational pull it has is huge. So these are some of the things that affect each other. So those are the physical quantities which are interacting with each other, and therefore orbital motion of a planet around a star is very much a physical phenomena, and it comes under the study of physics. Okay. So having said that, and having understood that, the next thing I want to discuss about is, when we talk about all physical phenomena in the universe, we're talking about a very huge range of things. It's not just a narrow subject. It is not just like the study of, let's say, an internal combustion engine of capacity of between 1000 and 2000 cc, which is through diesel or petrol, or it's not something very narrow like that. It's not something very specific. It is much more wide. So can we talk a little bit about the different areas of physics, the different branches of physics, or you can say the different subtopics of physics that range in this entire thing? Okay, so when we talk about physics, it is about all physical phenomena in the universe around us. Can you give me some examples of particular branches of physics or particular areas of physics?
There's theoretical physics, there is then experimental physics.
There is theoretical physics, there is experimental physics. What was the second thing you said, Beta?
Sir, electronics.
Experimental.
It's experimental physics.
Quantum physics.
Sir,
Particle physics.
Nuclear physics.
Astrophysics.
There is astrophysics. Somebody said quantum mechanics. Very
Sir,
interesting.
electronics.
There is electronics. Very good. Okay. Anything else?
Aerodynamics.
Thermodynamics.
Thermodynamics, aerodynamics. Very nice. Okay, now what is this? I mean, you can say kinematics, astrophysics, nuclear physics. I'm receiving some answers on text message also. So that's correct. Okay, now what is the smallest thing that physics deals with? Like if I'm going on a scale of larger to, I mean, smaller to larger things, which is the branch of physics which, yeah, sorry?
What did you ask?
What are the smallest of things that physics deals with?
Quantum physics.
Quantum mechanics.
So what is that branch of physics called, where we deal with the smallest of small things?
Quantum mechanics.
Quantum.
It is called particle physics. Okay, so particle physics is the branch of physics that deals with what we call the fundamental particles of nature, or better said is of matter. And these are the smallest of small particles. Okay, and you're correct in saying that quantum mechanics is very much part of particle physics, because quantum mechanics is, you know, that part of theoretical physics which explains the behavior of the fundamental particles of nature or particles of matter. Okay, when we come down to the smallest of small particles, like you might have heard of the term quarks. Anybody heard of quarks?
Yes, so it's the smallest particle. That's what makes up protons.
One of
and
the
neutrons.
fundamental particles.
Yes, very good. That's correct. These subnuclear particles, that is the protons and neutrons, when you break them down, the fundamental blocks of matter that we get are called quarks, right? And unlike protons, quarks do not have charge, but they have something called flavors. They come in 3 flavors. So the combination of quarks in a material, in a particle like a proton or a neutron, will determine whether it is a neutral particle like a neutron or whether it is a positively charged particle like a proton. Okay. Anybody heard of the term neutrino? It's one of the smallest particles known.
Yes,
Yes,
sir.
yes,
sir.
Yeah.
Yes.
So what can you tell me something about neutrinos? What is like particular? I mean, what is particularly interesting about neutrinos?
It is known as the ghost particle.
It is known as the
Ghost particle.
ghost particle. Yeah, very nice. Why is it called the ghost particle?
Sir, that I don't know.
Yeah. So
Has
this
no
comes back
electrical
to
charge and
one.
very small.
Sorry, Mansi, can you speak a little bit louder? I couldn't hear you.
So it has basically no electric charge and a very small mass, which can be negligible, even zero. And they are very abundant in the universe. Like they're everywhere. That's why they are known as ghost particles.
Yes, that is true. Okay. They are abundant. That is what Mansi says. They are present everywhere. One of the biggest sources of neutrinos is, you know, any nuclear reaction like the solar nuclear reactions that happen. So the sun is constantly radiating neutrinos, okay, which pass through all matter, including pass through the earth. Any source of radioactivity or radiation, nuclear radiation, whether it be like a, you know, nuclear power plant or any other such occurrence, also will have a flux of neutrinos. Now, the reason why neutrinos are called ghost particles is very interesting. And it brings us back to what we were talking about earlier, that does physics only involve things that we can see? In the traditional sense, when we say see, it means basically detecting of particles. Now, neutrinos are very, very hard to detect because neutrinos hardly interact with matter. Neutrinos, basically, they pass through matter, but they also exist in different states. Like in chemistry, you would have heard the term, you know, spin state of an electron in atomic physics, that the electron can have a positive or a negative spin state, or it has a spin quantum number of plus half or minus half. So that refers to the different states, the different quantum states in which fundamental particles of matter can exist in. So like that, neutrino also exists in different types of quantum states. And the only effect that, you know, passing through matter has on a neutrino is that it changes its quantum state as it passes through matter. So it takes very advanced detection techniques to to be able to detect neutrinos, and that happens only because the neutrinos, they change their state, or they change their quantum state as they pass through matter. The other thing about neutrinos which makes them very interesting is that they are one of the particles which have the lowest mass that is known in physics. They are almost massless. They're not massless exactly. Okay. When we talk about massless particles, we have another category which is called photons. You might have heard of the term photons, right?
Yes.
Yes.
Yes, sir.
Yes.
Particles of
Particles
light.
of light.
So in very simple language, we can say photon is a particle of light, but that is somewhat misleading. Okay, because when we use the term particle, we mean that it should have some non-zero mass, whereas a photon does not have mass. And since somebody was mentioning relativity earlier, okay, so there is also a principle in relativity that a particle or anything which has mass cannot travel at the speed of light. Any particle will always travel at a speed which is less than the speed of light. Whereas photons, as you know, are basically packets of light energy. So they travel at the speed of light. So a better description of a photon is that it is a quantum or a packet of light energy. Okay, yeah, I mean, we do say in everyday language, we say it is a particle of light, but basically it is not a particle in the traditional sense because it does not have mass. A photon rather is a packet of energy. It is a packet of pure electromagnetic energy, and visible light propagates in the form of photons, okay, packets of light energy. But it is not just visible light, but the entire electromagnetic spectrum. We have X-rays, we have ultraviolet, infrared, there is gamma radiation, there is microwaves, okay, there are radio waves, etc. So all these things together, they form what is called the electromagnetic spectrum. And all waves in the electromagnetic spectrum consists of packets of electromagnetic energy, which are called photons. So in that sense, even X-rays are not particles which are moving, rather they are photons which are in rectilinear propagation. Okay, only they are much higher in energy compared to the photons of visible light, and therefore they have much more penetration power, and in certain cases they can therefore have adverse effects. They can be dangerous. Similarly, we have gamma radiations which come from nuclear changes, and they are also much more energetic compared to X-rays or visible light for that matter. Okay, so coming back to the neutrino, so the neutrino is not completely massless like a photon is, but however, it has extremely small mass. It's one of the lightest particles known to physics, and therefore it had gone undetected in nuclear reactions for a very long time. If you study the history of particle physics, you will know that the detection of neutrino, or the discovery of neutrino, actually happened from the further understanding of beta decays. Okay, beta decays in nuclei, or beta reactions which happen at the nuclear level, and the discovery of the neutron resulted in the complete explanation of the physics of beta decays. Until the neutrino had been discovered, a certain puzzle was unsolved in physics, that how come in a beta decay it seemed that the linear momentum was not conserved when we considered all particles other than the neutrino. But the discovery of the neutrino resulted in the understanding that no, linear momentum as well as mass energy is conserved in a beta decay reaction also, like any other reaction. But because the neutrino has very small mass, it is very difficult to detect. Okay. Another particle you would have heard about is the Higgs boson, etc.
Yes, sir.
This is also
Yes,
called
sir.
the God particle. Yeah, it is a God particle. It's been discovered in the relatively more recent particle accelerator of the CERN labs, okay, which was specifically built to discover Higgs boson among other particles. So this is like the branch of physics that deals with the smallest of small things. Okay. Uh, Science has always evolved in various directions, and one of the directions in which science evolved is by trying to break down matter into smaller and smaller fundamental parts. For example, even before experimental science had started, when the ancient Greeks would try to, study science on the basis of pure logic and deduction. So they had come up with various theories. Like one of the theories was that there are four fundamental elements, earth, wind, fire, and water. Okay. That there are four elements that make up all matter. Now, of course, that was not correct. But the idea was correct that when we go on breaking down matter into smaller and smaller bits, there are certain fundamental building blocks of matter. So, in the absence of any experimental ability, the early philosophers, okay, science was part of philosophy at that point of time when there was no experimental science, there was no deductive science. So based on logical conclusions, these were the type of things that people were trying to develop. So from that far back itself, people try to understand that there must be certain common basic building blocks of all matter. And as science evolved and technology evolved with that, our understanding of the fundamentals of matter improved further and further. So we not only understood that all matter consists of molecules, and later that all molecules consist of atoms, and further later that atoms consist of the significant fundamental particles of electrons, protons, and neutrons. Right? Protons and neutrons form most of the mass of an atom, and protons give the nucleus the positive charge, whereas electrons gives the atom the property of negative charge. I mean, the electrons themselves have the property of negative charge. And with the motion of the electrons around the nuclei, we have the entire chemical properties of a particular atom. Okay? The chemical properties like the reactivity of the atom, whether it is electronegative or it is electropositive, the valency of a particular element, the nature of an element in terms of whether it will form covalent bonds or ionic bonds with other elements or with other atoms. All this is determined by what we call the atomic structure. And the atomic structure is nothing but the structure of the electrons in their orbital motion around the nuclei. And that is completely governed by the electrostatic force. Okay, so ultimately it is down to the physics of the atom. So anyhow, so taking the story forward, science discovered, particle physics discovered that atoms can be broken down into more fundamental particles. And these fundamental particles, why we call them fundamental is because they are the basic building blocks of matter. So whether we take electrons from oxygen atom or we take electrons from carbon atom or any other atom on the periodic table, all electrons are the same. They are fundamental particles. All protons are the same. All neutrons are the same. So it is just how we combine these particles into different types of atoms and how different types of atoms combine into different type of molecules. That determines how we have different types of materials. Like we have different materials in different states. H2O exists in solid state, crystalline ice. It exists in liquid state, water. It exists in vapor state. But when you break down H2O into smaller bits, you have atoms of oxygen and hydrogen. And you break them down further, you have electrons, protons, and neutrons. And they are same as electrons, protons, and neutrons from all other elements or from all other molecules or all other substances. So that was the kind of deductive experimental science that results in breaking down matter into smaller and smaller fundamental particles and understanding how combinations of these particles ultimately determine how matter behaves or determines the physical properties of matter, whether it be something like the conductivity of a metal, or it can be the heat conduction of different type of materials, or it can be the elasticity, it can be the tensile strength. So many different physical properties which are measurable, which are tangible, but ultimately they all depend on how these fundamental particles of matter are clustered about. So as physics progressed further, people wanted to understand that it's not just how protons, neutrons, and electrons are clustered together in an atom which determines the properties of the particular element, but it is also what determines the property of the proton, that it has positive charge, that it packs so much positive charge into such a small space. And also a proton is heavy, it has a lot of mass compared to something else like an electron. Okay, so fundamental science progressed further, particle physics progressed further, and we broke down the proton and neutrons into quarks, and subsequently we have more subatomic particles, subnuclear particles like neutrinos and Higgs boson, etc. So at one end of the spectrum, physics is dealing with the smallest of small things, which are extremely small. Okay, I mean, we are talking about things which are on the scale of it's hard to imagine how small a neutrino or a Higgs boson is. For example, just to give you perspective, what is the average atomic size? Can you tell me the order of the atomic diameter? An average atom, what is the size of the atom? What is the typical diameter? Anybody knows? Yes, it is of the order of what we call Armstrongs. The order of magnitude is Armstrong. That is, 1 Armstrong is 10 raised power minus 10 meters. So you can imagine how small this is. 10 raised power minus 10 meters is like 10 raised power minus 7 millimeters. Okay, so it is 1 upon 10 to the power 7. This much of a millimeter. So that is how small just an atom is. But compared to an atom, okay, a nucleus is even smaller. You know, like if this is the atom, then the nucleus will not even be a point. It's that small, because nuclear diameter is something much smaller. And that is an amazing fact about atomic physics, that most of the volume of an atom is actually empty space in which very light particles called electrons are moving about in circular orbits or in some kind of orbital motion. Whereas the entire mass of the atom, or at least the majority mass of the atom, is packed together in a very small space at its center, which is called the nucleus. Okay. And the nuclear diameter, yes, anybody can give me an idea about how much the nuclear diameter is? Nuclear diameter is of the order of magnitude of what we call Fermi. Have you heard the term Fermi?
Yes, 10
Yes,
raised to minus
sir.
15.
Yeah, how much is Fermi?
10 raised to minus 15.
Yes, so 1 Fermi is 10 raised power minus 15 meters. So you can imagine how small a nucleus is, you know, compared to an atom. It's literally, if the atom were like a world, okay, like a planet, then the nucleus is like a small particle at its core, because 1 Fermi is 10 raised power minus 5 times 1 Armstrong. So we're talking about a very small scale of things. And now the kind of particles that we are talking about, like neutrino or Higgs boson. Okay, now if you do a comparison of a nucleus with a neutrino or a Higgs boson, then it's an altogether different thing. Like if you're talking about the size of a small satellite like the moon or something, compared to the size of our entire solar system, how small the moon is compared to our solar system, that would be the typical type of comparison between the size of a neutrino and the size of a proton alone, let alone the size of the nucleus. So that is the scale of things that we're talking about in particle physics. Extremely small, okay, extremely abstract, right, and extremely difficult to comprehend. So that is how physics has progressed, okay, in terms of particle physics, and trying to understand, you know, the puzzle about the structure of matter, the properties of matter at a fundamental level, breaking it down into smaller and smaller bits. Okay. Now, if we talk about the other side of the range of physics, the other extreme end, that is, what is the largest systems that physics deals with? Okay, so you have answered the question already, because you have mentioned astrophysics, or I will also use the term cosmology. You heard the term cosmology, people?
Yes, sir.
What is cosmology? It is,
The study of cosmos,
yes, the study of our cosmos or of our universe. Okay. So basically, it is about trying to understand the secrets of the universe, the structure of the universe, trying to predict the history of the universe, how the universe evolved, how the universe was born, etc. Okay, so we have cosmology or astrophysics. Now, this on the other hand, so we are talking about neutrinos and Higgs bosons on one end, which are like extremely small particles, okay, so small that we cannot imagine. Whereas on the other hand, we have the cosmos or the universe or the astrophysics part, where we are dealing with such large distances. What is a common unit of distance in astrophysics?
Sir, AU.
Light years.
Light year, right? Okay. So in astrophysics or cosmology, for that matter, we have a unit of distance called light year. Now, one light year, how is it defined? It is defined as the distance traveled by light, right? In one single year, or I should say in a whole year. So that distance is equivalent to 3 lakh kilometers per second, or I can say 3 into 10 raised power 8 meters per second, multiplied with 60 seconds, that's in 1 minute. Okay, multiplied with 60 minutes, that's in 1 hour. Multiplied with 24 hours, that's in 1 day. Multiplied with 365. So this is 1 light year in meters. So you can imagine it's a staggering amount of distance. Okay, so on the one hand, we had the size of the nucleus, which was 10 raised power minus 15 meters, 1 Fermi. And on the other hand, we have 1 light year, which is such a huge distance. And when it comes to size of the universe, you know that 1 light year is actually a very small unit. Now, we have galaxies which are basically millions of light years away. So you can understand how staggering a distance we are talking about. Millions of light years away. That means it takes light 1 million plus years to travel from one point to another when we are talking about the distance between such galaxies. So one of the amazing facts is that when we look into the night sky through a telescope or a naked eye or whatever, okay, we are looking back in time. Looking into the night sky or looking into the cosmos, when we observe distant stars, galaxies, etc., we are looking back in time. Is that true?
Yes, sir.
Yes,
Can
sir.
you explain what I mean by this term, looking back in time?
Sir, light takes 8 minutes to travel from the sun to the earth. So like
Yeah,
if
it
we are
takes
looking
8
at the
minutes.
sun,
That's
we are
correct.
looking 8 minutes back.
So that's very correct. So for example, the sun is at a distance of 8 light minutes. Okay. That means right now, if we look up into the sky and see the sun, what we are seeing of the sun is 8 minutes back in its history, right? Because light that we are receiving from the sun just now had started from the sun, had started from that source, not just now, but 8 minutes back. That means we have no idea of exactly what the sun is like right now. We only have an idea of what it was like 8 minutes back when we are looking up at it. Now, similarly, when we suppose we look at a star, which is, let's say, 200 light years away. Okay. If you study cosmology, you'll see 200 light years is actually no big deal. It's relatively, it will be one of the stars which is closer to our solar system, very much within our galaxy, etc. There are stars which are much far further away, or galaxies which are much further away. So 200 light years away means what we are seeing of the star, okay, means we are looking at that particular star 200 years back in time. because the light that we are receiving, that is the information we have about the star. There is no mode of communication or no mode of information transfer known to mankind which can travel faster than the speed of light. So the light that we are getting from that star, to detect it, to see it, so-called, to understand its condition today, okay, that started 200 years back. So there is no way of knowing what has happened in these 200 years, because there's no other form of communication. There's no other form of information transfer, which is faster than 200 years. I mean, which is faster than light. So we have no information which is more recent than 200 years about that star. So if you think about it, it's a very staggering thought, that it's a thought that makes us very humble, that, we are actually very tiny and very insignificant in terms of the entire universe around us. And that tells you another thing about the range of the subject of physics. At the upper end of the range, when we're talking about cosmology, we are literally talking about things which are, so large that they are basically approaching infinity. Now, when we talk about the term infinity, is what is infinity in mathematics? It is a number that is so large that we cannot comprehend that number. No, we cannot write it down. We cannot quantify it. That is why we say that one of the properties of infinity is that infinity plus some number or infinity minus some number is equal to infinity. Okay, if we have a chain, like a metallic chain which has links, if we say that the chain is infinitely long, it means that it has so many links that if we were to remove 2 or 3 links from it, or if we were to add 4 or 5 links to it, it would not make any difference to the length of the chain at all. It would still remain infinitely long. So infinity is something that is so large that it is beyond comprehension. It is something that we cannot quantify. We cannot give it an exact value because it is larger beyond imagination. So we can say that the universe or the upper range of physics deals with things which are infinitely large. And similarly, we have another term in science which we call infinitesimal. Infinitesimal is something which is the opposite of infinite. Infinite is something that is extremely large. Large beyond comprehension. A physical example of that would be the size of the universe. Okay. It is large beyond comprehension. Now, similarly, we have the opposite end of that, a term called infinitesimal. It basically, one way of saying is that it is infinitely small. Okay. Something that is so small that it cannot be compared. Okay. And in a certain sense, we might say that the smallest of particles that physics deals with are truly infinitesimal because their size is so small that they cannot be comprehended. Okay. Now, the interesting thing is physics is not only dealing with these two extremes of particle physics and cosmology at the other end, but everything in between. Okay. And because it deals with everything in between, you can say that it deals with all physical phenomena in the world around us. So there is literally physics in everything.
Sir, can you scroll up for 1 second?
Yeah, just a moment. Some particular point you want to discuss, Beta?
No, I wanted to see.
Yeah.
Thank you,
So
sir.
what is
I'm
that
done.
written?
Which
Sun is at 8 light.
8 light minutes. Okay. The
Okay, sir.
sun
Thank you.
is at a distance of 8 light minutes. Okay. That means the distance between the earth and sun, that is equal to how much? It is speed of light into 8 minutes.
Yes, sir.
Okay. All right. So when I say physics is in everything, okay, what I want to sensitize you to is the fact that entire technology, in a sense, is built on physics. Okay. Whether we are talking about, microelectronics, or we are talking about, heat engines and thermodynamics, or we are talking about, let us say, biotechnology. Okay. Everything has all physical processes which involve physical quantities, involve physics at some level or the other. Okay. Now, the other thing we were talking about earlier was that the method of physics. It's all very good to say that physics deals with all physical quantities. It is the study of all physical phenomena. But obviously, physics relies on certain methods. Okay. And some of you have given like hints about that when we were discussing about what physics is. So, for example, one of the things about the method of physics is that physics develops mathematical can say models, okay, through equations for any physical phenomena. So mathematical modeling is something that is very much part of what we call the method of physics. Okay. So for example, when we use the equation V is equal to U plus AT, okay, when this equation is used. This is used for motion along a straight line, right?
Yes.
But under what condition? Most important, with uniform acceleration. The acceleration of a body is constant, okay, and its initial velocity is u, and it's moving along a straight line. Then we explain that its velocity after a certain time t becomes v, which is u plus at. Or we can also, so this is nothing but a mathematical model. I mean, it's a very complicated word I'm using. The simple word to use is it's an equation. So this is a mathematical equation, okay, which is relating to physical parameters. It relates two physical quantities, velocity with time, okay, on the basis of two other properties that the system had, two other physical properties. One is the initial velocity u, and the other is the uniform acceleration e. So this mathematical equation, you can say itself, is a way of developing, it develops a mathematical model of the system. And in this case, what is a system? It is nothing but a body or particle in uniformly accelerated motion along a straight line. Okay. But for example, we can do more with this. To understand this equation better, we can convert it into a graph. So if we convert it into a graph, we will see that we have this kind of a shape. If we put velocity on our vertical axis, and if we put time on our horizontal axis, okay, then we can see that this particular relation v is equal to u plus at. It can be a line like this. Okay. So let us say this is for a particular body. It is for body 1. But let's say we have another body which is having the velocity versus time like this. So when we put together this information in the form of a graph, by observing the graph itself, what we can say over here, we can do more analysis. We can understand, for example, that in this case, in this example, what is happening, bodies 1 and 2. What can we say about the initial velocity? From the graph, they are same. We can see they are having initial velocity same. But what about their accelerations? From the graph, what can I say about the acceleration?
Body 1 has
Body one has
body
more
one has more
acceleration.
Very good.
acceleration.
By observing this, I can see that body 1 has more acceleration compared to body 2. I can understand that by various things. Okay, if I get into the mathematics of a straight line graph, I can understand that the acceleration is what we call the slope of this graph. No? It's a y equal to mx plus c kind of graph. So I can see that the first blue colored line has a steeper slope than the second one. So from that, I can say that the acceleration is more. But I need not go into something that complicated. What I can just say is that at t equal to 0, both of them are having the same u. So that is showing me that u is same. But at any other time, if I see, whether I'm looking at this time or this time or this time, at any other time, if I see, I can see the value of the velocity that this one is having is more than the value of the velocity that this one is having. Okay, so from that I can see that at any time u is same, but at any time t greater than 0, the v1 is greater than the v2. So that is showing me that e1 must be greater than e2. Okay, so this is another, what I'm trying to explain is what mathematical modeling is all about. Okay, we convert a given situation. So I could have started with these words that, two bodies are moving along a straight line with uniform acceleration. Both have the same initial velocity, but one has a greater acceleration than the other. So that is like a descriptive analysis of the situation. But the moment I convert that descriptive analysis into a maths equation, or I convert it into a graphical analysis, we are doing what is called mathematical modeling. And the mathematical modeling makes the analysis much more precise. It makes it much more compact also. And it makes it possible for us to analyze the given situation in much, much more detail than we would in terms of description. For example, at a different level, we can take an example like this. Now, suppose I'm talking about an electrical circuit. Okay. So of course, this in itself is full of physics. Okay. An electrical circuit will be driven by some kind of a voltage source, whether it's an electrolytic cell or it is a photovoltaic cell, or it can be driven by even an alternating current generator. It might not be a DC circuit, it might be an AC circuit, etc. So the whole process of the generation of potential difference, that itself is physics. Okay, but I'm bypassing all that for the moment. Let's say I have a battery. Okay, I'm not concerned with whether the battery is a dry cell or it is an electrolytic cell, or it is a photochemical cell or whatever. Okay, so I have, let's say, a battery which has what is called an EMF of something, let's say 20 volts. And I've connected to that a combination of different devices. And the property of the device which is important for us over here is the resistance. Okay. So this is something that you're familiar with. So I have 3 resistors. Okay. So given that resistors are like this, let's say this is 3 ohms, this is 6 ohms, and this one is 2 ohms. Now I want to find out, okay, the current through, or first of all, I want to find out the equivalent resistance. Okay, we'll come to currents and all that later. I want to find the equivalent resistance. Then I want to find out the current that is drawn from the battery, the current that is going through this resistor. So I want to find out I and I2 specifically in amperes. Okay. And I also want to find out the voltage across the resistor R3. Okay. So before coming to solving this, again, why I'm taking this example is to show you that you're already familiar with this process of mathematical model. Now, I could have described the system by just telling you that I have connected 2 resistors R1 and R2 in parallel, and that combination I've connected with R3 in series, and I've connected that across a 20-volt battery, and I want to find out all these things. But by drawing a circuit diagram, okay, by drawing a circuit diagram, I've already created a mathematical model of it. Okay, and now whatever formula that you have learned for the combination, for the relation between current and voltage which is basically Ohm's law. So some of the things that we'll be using here are the application of Ohm's law. Okay, that is the voltage across a resistor is equal to the current going through it multiplied by its resistance. Then you will be using the formula for combinations of resistors. We'll be using for series combination. We'll be using for parallel combination. So all these formulae and all these equations that you are using, they're nothing but mathematical modeling. And it is through that mathematical modeling only that we can give precise answers like this. That if we connect a voltage of this much across these resistors, then exactly how much is the current passing through? We can do a more precise calculation of what is the rate of energy supplied by the cell, that is the power supplied by the cell. What is the rate of heat dissipation at the resistors? So these are precise measurements, or these are precise calculations of actual physical quantities, actual physical parameters that would be happening in this actual physical event. This is actually a physical phenomena. If we actually do this in the lab, it is something which is nothing but a physical phenomena. And the different physical quantities which are affecting each other are very much these things: the resistances, the voltages, the currents, the powers, the heat dissipations, the rate of heat dissipations. So the prediction about all these physical parameters, how they affect each other, that can be done very precisely by using mathematical modeling. So that is what I mean by saying that the method of physics is very much dependent on the ability to do mathematical modeling. Okay, so anyway, just let's do this as a practice question. You can start sending me the answers if you're clear with this question. If you have any doubt regarding the question, you can send that to me also. Yes, Anirudh, Mansi, your answer is correct. Parv, your answer is also correct. Vineet, your answer is correct. Very good. Arya, your answer is correct. Okay. Now I'm starting to look at all the answers. Yes, Darsh, your answer is correct. Shaurya is correct. Okay. Okay, now there are various different methods by which we can solve this situation. Okay, let's get into it in detail. Now, for example, one of the methods, which is a very common method in physics, is reduction. We can reduce the given event into simpler events. Okay, by using the combination of equivalence. Okay. So the method of reduction, okay, that is, we want to convert it to an equivalent circuit with a single equivalent resistance. Okay, convert the circuit, given circuit into that. So for that, what we understand is that if this combination is drawing a current I like this over here, okay, that current is first breaking into two currents I1 and I2, and then recombining into the single current I. So we can see that R1 and R2 are in what we call parallel combination. Okay, so R1 is in parallel to R2. Okay, so we can replace this combination of R1 and R2 with a single resistor of, let's say, R prime. That will be equal to R1 R2 divided by R1 plus R2, because I know this formula from before. I know that 1 upon R prime is equal to 1 by R1 plus 1 by R2. Now, what is the logic of this? We can get into that later. But this is the formula. So I've already done some mathematical modeling earlier. This is the formula for parallel combination. Okay, so I know that. Okay. So having done that, I can see that this will become. Now remember, R1 was 3 ohms, R2 was 6 ohms, and R3 was 2 ohms, right? These were the values. Just verify that from above. Yeah, 3, 6, and 2, and this was 20 volts. Okay, very good. EMF was 20 volts. So using these values now, I can directly see that this R prime will be how much? This R prime will be 2 ohms. 1 upon R prime will be 1 by 3 plus 1 by 6. So that will be 1 by 2. So from that I get this. Okay. Now the next, so next thing what I'll do is I'll be able to, so what I'm saying is it's a reduction method. We are able to convert into a circuit with a single equivalent resistance. So in step 1, we will reduce it to something like this now. The combination of those two resistors is reduced to a single resistor. So we know that this circuit is equivalent to this circuit. So whatever current this was drawing from the battery here, the same current I is drawn over here. Now, next thing we can see is that these two resistors are in what we call series combination. Because same current is passing through them. So we have a formula for series combination that R equivalent is going to be R1 plus R3. This is the formula for series combination. Now, in case we don't know where this formula has come from, then it becomes a matter of great wonder for us that how we can say this. What is the logic behind this statement? So that's a separate matter. We'll come back to that. But we have built that mathematical model already. So we can use that mathematical modeling for reducing this circuit by step 1 into this circuit, which has 2 resistors, and then by step 2 into another circuit, which has only a single resistor. So now step 2 now, we are able to reduce it to a single equivalent resistance. Which is connected to the same cell. Okay. And therefore it is drawing the same current. So by the calculation now we can see that this R equivalent is equal to, this was 2 plus 2. So it is equal to 4 ohms. Okay. And the EMF was 20 volts. So now we can use Ohm's law. And we can see that the potential difference across this resistor, let's say this point is A, this point is B. So delta V, which is VA minus VB. Okay. On the one hand, it is equal to the EMF of the cell, and on the other hand, it is equal to I into R equivalent. So the EMF of the cell should be equal to I into R equivalent. So from that, we can see that the current will be equal to the EMF 20 volts divided by the equivalent resistance, which is 4 ohms. So we'll get the current in 5 amperes. Okay, so that answers the second question for us also. The net current drawn, I, is equal to 5 amperes. Okay. Now, of course, there are other methods of doing this also, and we'll come back to that. But this is the simplest way, because in this we are using the mathematical model of, so mathematical model is just a fancy word for formula in this case. We're just directly using the formula for series and parallel combination. And using that, we are reducing the circuit to an equivalent single resistor. So this kind of process is something which is very common and very important in physics. We want to reduce a more complicated situation to a single equivalent situation by using some kind of mathematical modeling. Okay. Now the next thing we want to do. So I hope this is clear to all of you people. Anybody has a doubt up to this point where we've calculated the equivalent resistance? So far, what we've done, we've calculated the equivalent resistance of the situation as 4 ohms, and we have got the current drawn from the battery to be therefore 5 amperes. So if anybody has a doubt up to this point, please let me know. Okay, now let's come back to our, what else we want to calculate. We want to calculate I2. So now the interesting thing is how we will calculate the value of I2. So to calculate I2 now, we will need to use the property of Ohm's law, but not in this circuit. Okay, we cannot use that in this final circuit that we've drawn, or even in the step 1 circuit. We have to go back to the fundamental circuit, which was the original circuit. And in this, we have to understand what the value of I2 is. Okay. So I've got a lot of answers. Okay, let me check out if I've got the correct value of I2 from anyone. Just try it out. In the meantime, I'm going through your answers. Okay, so many of you got the value of I2 as 10 by 3 amperes or 3.33 amperes. But I just want to check, I want you to check your solution once more.
Sir, can you scroll down?
Sorry, come again, beta.
Sir, can you scroll down?
Scroll down. Yeah, I can scroll down. I'll actually minimize this a little more and I have to find I2. Yes, Kirti, that is correct. Ayush, that is correct. Yash, that is correct. So finally, I'm getting some correct answers. Very good. Shubham, that is correct. Very good. Anirudh, correct. Parv, correct. Okay, so I'm just giving you the value of I2 first. Try to figure it out yourself. Okay, you should be getting I2 as 5 by 3 or 1.67 if you approximate amperes. Okay, some of you have got this correct, but some of you have also got the wrong answer. For some reason, you might have got double of this or something. So I'm just going to explain in a minute how we get this I2 equal to 5 by 3. But try to figure it out yourself once. Okay, so now I'm going to give you the explanation of why I2 is equal to 5 by 3 amperes. Okay, because many of you don't seem to have got that answer. Okay, so what I'll show you is even before the value of I2, I'll show you how that actually comes. If you are clear about the concept of parallel and series combination, you will find it easy enough to find the value of I2. Okay, so let's look fundamentally. So let's look at the fundamentals of series and parallel combination. So in a series combination, how do we recognize a series combination? We should have a branch in which two resistors have the same current. Yes, that's correct, beta. Same current. Okay. So if these 2 points are A and B, and the middle point between them is C, we can see that apply Ohm's law, that is delta V is equal to IR. Okay. So apply Ohm's law to resistor R1. So that is across AC. So we'll get VA minus VC is equal to IR1. Okay. And then apply it again across CB. So we'll get VC minus VB is equal to IR2. Okay, so let's say this is our equation 1 This is our equation 2. Now combine them. So you are basically applying it across AB. So if you add these two equations, you'll see you'll get VA minus VC plus VC minus VB. So you'll get VA minus VB, and that will become IR1 plus IR2. So this VA minus VB is becoming equal to I into R1 plus R2. So we should say that is equal to I into equivalent resistance across AB. Okay, so we can see that we are reducing this to a single equivalent resistor, let's say RAB. Okay, and that should be having the same current when we connect it across these same 2 points A and B, whatever potential difference we've applied. So from this we can now see that okay, the equivalent resistance is equal to R1 plus R2. Okay. And one more thing that we can see is that so this is the fundamental aspect of series combination. Okay, and one more thing that we can see from here, that delta V1, that is the potential difference across the first resistor, that is IR1, and delta V2, the potential difference across the second resistor, is IR2. So if we now divide these two, we can see that the ratio of the potential differences is R1 is to R2. So this is also an important fact. Okay. So for example, if we connect, let's say, a 200 ohm resistor in series with a 100 ohm resistor, okay, across a 60 volt battery or a 6 volt battery, let's say. Okay, so straight away we can see that the current drawn will be EMF divided by equivalent resistance. So that will be 6 divided by 300, that's 1 by 50, or that is 0.02 amperes. Okay, and we can also see that the potential difference across this resistor, delta V1, and this resistor, delta V2. Okay, so we can see that delta V1 is to delta V2 will be R1 is to R2. So that will be 2 is to 1. And delta V1 plus delta V2 will be equal to 6 volts. Okay, so we can see that delta V1 will be 2/3 of 6, or it will be 4 volts. Okay. And delta V2 will be 1/3 of 6, so that will be 2 volts. So not only we are getting the current drawn by the combination, but we are also seeing that this helps us find out the what we call the distribution of voltage. Okay, so this tells us about the distribution of potential in series combination. Okay. The total potential difference divides in the ratio of the resistances, R1 is to R2. So that is the complete physical explanation, okay, of the series combination formula, albeit using another fundamental formula, which is Ohm's law. Okay. Now, where Ohm's law comes from at this stage, you can just understand experimentally. Okay, that if we take a resistor and put it across a variable voltage source, okay, you might have done the Ohm's law experiment in lab also. Okay, it's very easy to verify Ohm's law because it's an experimental fact. It's how metals behave. It's how resistance behaves. Okay, Saud, you have asked me the question about the neutrino again. So while others are noting down this part, I will just go back to that. Neutrino is called ghost particle because it's literally invisible. Okay, it is called a ghost particle because it had proved to be invisible for many decades in physics before people understood what exactly happens when a neutrino passes through matter. It does not react with matter in any way like a traditional particle does. Okay, instead it only undergoes a very subtle quantum mechanical change of state itself. So detection of neutrino is something very, very complex and something that had not been achieved for many decades in physics, even after the discovery of neutrino. So while neutrino had been discovered in certain situations, but neutrinos, the abundant neutrinos that are all around us all the time, I was telling you earlier, solar neutrinos are constantly being emitted by the sun, etc. There are neutrinos that are part of cosmic waves, etc. So these neutrinos are present all the time around us abundantly. Now it's very, very hard to detect these neutrinos. They literally go undetected. They are literally invisible to matter. So those are the properties that a ghost has. It's like you can say a ghost is something that has no physical presence. So neutrinos are almost like that. It's very hard to detect their physical presence. So that's why they were nicknamed the ghost particles. Okay.
Okay, sir. Thank you, sir.
Sorry, but I'm not able to hear you. Can you speak a little louder? Okay, so hope that explanation is clear. Now coming back to this, let's also first look at the fundamentals of parallel combination. Then we will get back to that question. So in a parallel combination, as you know, multiple resistors, in this case, I'm just sticking to two resistors. Later we will see more than two resistors also. If we connect them across the same potential difference, so these 2 points A and B, they are connected across the same two resistors. So whatever current is being drawn from the point A, let's say, it gets divided between the two resistors. And these currents again combine here. Okay. So you can see that delta V1 is equal to VA minus VB. The potential difference across the second resistor is also equal to VA minus VB. And this is equal to I1 R1. This is equal to I2 R2. Okay. So they have common potential difference instead of having common current. Okay. So now we can say that the net current is equal to I1 plus I2. Where does this statement come from? Can anyone tell me? What is the logic behind this statement that I is equal to I1 plus I2?
Because, sir, in a parallel circuit, the current gets split.
Current splits, current divides, that's correct, beta, but there must be some other physical reason why it's exactly equal. I'm saying why, for example, I can be larger than I1 plus I2. ऐसा क्यों नहीं हो सकता है that I is
the amount of current does not change.
Why the amount of current does not change? I'll give you a hint. Is there any conservation principle involved?
Yes, sir.
Conservation of what?
Because the current entering the parallel combination and the current leaving the parallel combination has to be same.
Yeah, but the conservation
The
principle
law
involved, it is
of conservation
charge.
of energy.
Of charge, beta. Because see what is happening now, current actually kya hai? Current is a stream of electrons which are flowing in the opposite direction. So there are a stream of electrons flowing like this. There are a stream of electrons flowing like this. And there are a stream of electrons flowing like this. Okay. But this point over here, this junction point which are drawn here, this point, it cannot accumulate electrons. Electrons will neither be created nor destroyed in a circuit. They'll only be circulated from one point to the other. So at any point, neither electrons are getting generated nor electrons are getting this thing, destroyed or accumulated. So the total number of incoming electrons, which is proportionate to I1 plus I2, must be equal to the total number of outgoing electrons, which is proportional to I. So this actually comes from conservation of charge. Conservation of charge, or you can say total number of electrons in the entire circuit. Total number of electrons will remain conserved. It is only that they are being continuously moved, continuously be circulated by the voltage source. So, obviously I must have connected some voltage source like this. Otherwise, I could not achieve this potential difference. So if this EMF is E like this, then my VA minus VB is equal to that E only. So this voltage source is only doing the necessary work through its chemical potential or whatever other source of voltage is there to continuously circulate the electrons. Okay, but the total number of electrons in my circuit is remaining conserved, which is why we have this junction law. This principle is clear to all of you people?
Yes, sir.
Yes, sir.
Okay, very good. Okay. So there is always some logic, there is some underlying principle behind every equation. Okay. So now when I apply this equation to these, apply this concept to these two equations. Okay. So from equation 1, you can see that I1 is delta V by R1. And from equation 2, I can see it is delta V by R2. Okay. Where basically I'm saying that delta V is equal to VA minus VB, which in this case is the EMF of the battery. Okay. So I have this, and I should say I is equal to this potential difference between EB divided by some equivalent resistance.
Sir, I have one doubt.
Yeah, tell me about that.
So what does that arrow mean? That dotted arrows which you have made?
The dotted arrow is actually the flow of electrons.
Okay, sir.
And they are opposite, no? Actually. So it is
Yes.
because of historical reasons that we take the flow of current as the, assuming there is some positive charge which is flowing, because current was discovered before electrons were discovered. It's one of those interesting things in science. Okay.
Yeah.
So that is the flow of electrons. Okay. In later in class 12, we will learn there is something called drift velocity. It is like the average velocity with which the electrons are flowing inside the conductor. And that average velocity or drift velocity also depends on the potential difference. So it is a property of the conductor that how much resistance it has, how much free electron density it has, etc. That will determine the drift velocity, and from that the current.
Okay, sir.
So you can think of potential difference as some, it is some kind of physical quantity which pushes electrons from one side to the other, from negative potential to positive potential. And that pushing causes them to move with a certain average velocity, which is called the drift velocity. And that drift velocity is proportional to the amount of current, therefore, through the conductor. So actually, there is a basis for Ohm's law also, which we will be studying in class 12, that V is equal to IR. Okay, that involves some more terms like drift velocity, free electron density, etc. Okay, so now when we examine this equation, we can see what this is saying. This is saying that our equivalent resistance is such that 1 upon R equivalent is equal to 1 by R1 plus 1 by R2. So this is the logic of this formula, okay? Because once we have written our equation 1 and 2 above using Ohm's law, so in this we are basically applying Ohm's law to each resistor, each of R1 and R2. So now we can see that this combination is equivalent to a single resistor connected to the same points A and B, let's say. So this would draw the same current. Okay. So for that to happen, the single resistor should have a resistance like this. That's the first thing. And the second thing to observe, okay, is about the current division. Now this is very important. Division of current in a parallel combination. This is what will help us solve that second part. So division of current is such that, of course, I is equal to I1 plus I2, we know that. But also from equation 1 and 2, we have delta V is equal to I1 R1. Okay, that was equation 1. And delta V is equal to I2 R2. That was equation 2. Where delta V is basically this thing. It is VA minus VB. So from these two, I can see that I1 is to I2 is equal to how much? R1 is to R2. We just divide these two equations or just equate them. So from that you will get this. So division of current happens in such a way that the current divides in a ratio proportional to the ratio of the resistances. Oh, sorry, inverse to the ratio of the resistances. I1 R1 is equal to I2 R2. That means I1 by I2 is equal to R2 by R1. So this becomes important. So now, for example, if I have this combination of, let's say, 6 ohms and 12 ohms, and I've connected that across a 30 volts battery. So first of all, I will see that equivalent resistance here will become how much? It will become 4 ohms. 1 upon R equivalent is 1 by 6 plus 1 by 12. Okay, that's the first thing. Okay, so I will become 30 divided by 4 or 7.5 amperes. Okay, now once I understand this, this will also become important. Okay, so this concept applied here will tell me that I1 plus I2 is I, which is 7.5 amperes, but I1 is to I2 is R2 is to R1. Okay, so this one is R2, this one is R1. Okay, so it is 1 is to 2. So that means I1 will be 1/3 of I. So it will be 7.5 by 3 or 2.5 amperes. And I2 will be 2/3 of I. So it will be 5 amperes. So this also becomes an important part of the analysis of the parallel circuit or the parallel combination. Not just that the equivalent resistance is R1 R2 divided by R1 plus R2, or 1 upon equivalent is 1 by R1 plus 1 by R2, but also the division of current. This is about the division of current. Okay, so hope this is clear to all of you.
Yes.
Yeah, Shreya, okay. I'll show you the series circuit again. I'll send you the notes for this, so don't worry. I will send the recorded lecture as well as the notes that I'm writing on this whiteboard now. I will send you a copy of that, so don't worry. And in any case, like, this is not like we're not really started the syllabus. We'll be starting with a different chapter altogether next week. This is just my discussion with you about the method of physics. So through something that you're familiar with, which is, basic things like straight line motion, then circuit equations, etc. I'm trying to explain the general method of physics, which is mathematical modeling, right? Okay. So now if I come back to my earlier circuit now, so we had seen that we had got the equivalent resistance in that problem. We had got the equivalent resistance to be 4 ohms, having connected to a voltage source of EMF 20 volts. So we had got the current in the circuit to be 5 amperes. Okay. Now if we go one step back, this was the combination of R prime and R3, where R3, if you remember, was 2 ohms and R prime was also 2 ohms. So now in series combination, remember, the current is common. So the same current I is passing through both of them. But now if I talk about the potential difference, if I take this as delta V1, let's say, and I take this as delta V3, okay, or if I label these points as A, B, and C, you can see that delta V1 is to delta V3, or potential difference across AC is to potential difference across CB. That will be R prime is to R3. In this case, it will be 1:1. And VAC plus VCB is equal to 20 volts. So this is also giving me the additional information that the potential difference across AC is going to be 1/2 of 20 or 10 volts. Okay. Though this was not asked in the question, whereas this was asked. This was this third part, VCB. This is the potential difference across the resistor R3. Okay. That is also 1/2 of 20, or it is 10 volts. So I'm coming to the division of current also, but this was the third part of the question. The potential difference across the resistor R3, that will be this. Okay. And then we will take it one step further back from this, where we have the whole circuit. So when we take it one step further back, the original circuit that we had, that was like this. So now we'll apply the concept of division of current in a parallel circuit. So this same current I, which we got here, which is 5 amperes, it's coming back here, it's coming back here, but it is dividing into I1 and I2. So we have I1 plus I2 is equal to I, which is 5 amperes. Okay. And now R1 and R2 in parallel. So I1 is to I2 will be equal to how much? R1 is to
R2.
So that in this case is, this was 3 ohms. Okay, this was 6 ohms. This was 2 ohms. So this ratio is becoming how much? This ratio is becoming 1:2. Okay, so this is the important thing. Okay, so our second equation will tell us that I1 is 1/3 of I. So that's why it is 5/3 amperes. And oh, sorry, my mistake. Wait. It is inverse ratio. My mistake. I1 R1 is equal to I2 R2 now. So this should be R2 is to R1. Okay. So what basically you have is in parallel combination of R1 and R2, we have labeled these 2 points as A and B, no? This point and this point. So you can see that potential difference across AB is I1 R1 equal to I2 R2. Okay. So from this you can see that I1 by I2 is R2 by R1. So this should be 2:1. Okay. So from this we can see that I1 is 2/3 of I or 10 by 3 or 3.33 amperes. Whereas I2, the current in the 6 ohm resistor is 1 by 3 times I. So it is 5 by 3 or 1.67 amperes. So this was the question that had been asked in the B part. Okay, so again, this is about understanding the mathematical modeling of a complex circuit with 3 resistors. Okay, you're reducing it first to 2 resistors, then to a single equivalent resistor. But also you're using the properties that we saw during this formula development or during this equivalent circuit method. So we are using those formula also to understand how the current division is happening between R1 and R2. The current I is dividing between I1 and I2, and also how the potential division is happening between the points A, C, and B. The potential difference of 20 volts is divided between the combination AC and CB. So the potential across AC and the potential across CB is in ratio of those resistances.
Sir, I have one doubt.
Yeah, tell me better.
So in that example which you shown for that parallel combination,
Yes, sir.
so sir, in that I have a doubt. You had written I1 plus I2 is equal to I, which is equal to
Yes,
7.5 ampere. So how did we get that
yes.
7.5 ampere?
How we got that in the earlier example? Na? So that was a different
Yes,
numerical example where the resistors were how much? Where
6
is that
ohm and 12
example?
ohm.
Yes. Okay. So this is how we had got this. Okay. So this is a different problem. So let me put that aside. So in this example, what was happening is, so how we got that I is 7.5 now. So see, this is how we got it.
Yes,
We got the equivalent resistance as how much? 4 ohms. Okay, that is coming from this formula. 1 by R is equal to 1 by R1 plus 1 by R2.
yes,
Okay, so this is clear.
yes sir.
Okay, so 1 by 4 आ गया, that means R equivalent कितना हो गया? 4 amperes.
4 ohm.
Sorry, 4 ohms. Now
Yes sir.
we are connecting that across how much voltage? If you draw this as an equivalent circuit, that R equivalent is connected across how much voltage? The EMF of this cell,
Yes.
and that EMF was 30 volts. Okay, so you understood now
Okay.
how we got the R, how we got
Okay
the
sir.
I now. Okay,
Yes
so
sir.
this
Got
was
it.
the next
Thank you
step, that
sir.
we calculated the I as EMF divided by equivalent resistance. That's how it became 30 by 4.
Okay sir. Yeah.
Clear now? I'll scroll down.
Yes sir.
Okay. What about this question is clear now? How we got these two currents?
Yeah.
Okay. Okay, so that almost brings us to a conclusion of today's lecture. But before we conclude, I just want to give you a sort of introduction to what we'll be doing in the next lecture. So, in the two examples that we saw above, where one was an example of straight line motion, the two graphs we had drawn and all that, and the other was electric current. Okay, so one thing you'll see in these examples, for example, this one above, the physical parameters we dealt with, like voltage, resistance, current, etc. These are physical parameters which are called scalars. They are physical quantities, physical parameters or quantities called scalars because they have only magnitude, okay, and no direction. How I know that? For example, if I am having a situation like this, where this current is 1 ampere and this current is 2 amperes, then this current I is I1 plus I2, that is equal to 3 amperes. Now this is what we call a scalar addition, because we are not taking direction into account. If I change this situation to something like this, that I1 is coming from this direction, I2 is coming from this direction, and I is going out from this direction, it would have been the same. It would not affect the answer in any way. So you can see it's the same because it is not affected by direction. A scalar addition is, it does not take direction into the analysis. Okay. Similarly, whether I have two resistors in series like this, or they can be in series like this. The equivalent resistance will still be R1 plus R2. Doesn't matter at what angle we have connected the resistors. So REB, in both cases will be R1 plus R2. So this is again an example of scalar addition. Why? Because resistance was also an example of a scalar quantity. Okay. But there are certain physical quantities which have significant direction. So this is what we will start with in the next week. That physical quantities can be divided into two categories at this stage: scalars and vectors. Okay. Now, vectors are quantities which have both magnitude and direction. A good example of this is displacement. Okay. Now, to understand why displacement is a vector, let's look at two situations. Okay. One is that a person first makes a displacement of 20 meters like this, okay, and then makes a second displacement of 15 meters like this and reaches here. Okay. So if this is what his initial position was, and this is what his final position was, can you tell me what is the net displacement?
35.
35 meters.
5 meters.
Yes, you can see that the net displacement is equal to 35 meters. Okay. But now consider the same thing in a different example. Okay. So what the person is now doing in this second example of mine is that he is first making a displacement in this direction of the same thing, 20 meters. So he reaches here. But now for his second direction, now let's say what I'm observing is, the diagram from top. So he's actually walking on the ground. So what I'm seeing is directly from top, I'm seeing the ground. Gravity is going into the plane over here. The vertical direction is coming out of the plane of the paper. So his second displacement, he goes like this at 90-degree angle and reaches here like this. Okay, so this is my directional sense. This is north, south, east, west. So he first goes east through a displacement of S1, and then he goes north through a direction of S2, through a displacement of S2. And now this is his final position. Okay, and this is, yes, you can see his, okay, so now his initial and final displacement are such that, I mean, initial and final position are such that, as you have all correctly said, the net displacement is this one.
5 meters.
You can see that the net displacement here, it happens to be square root of 20 square plus 15 square, and that is also because this angle is 90. It happens to be 25 meters, right? So that shows us that the same magnitude of displacement is 20 and 15, but can give you different resultant displacement when the direction is changed. Same thing if I had done now like this, that suppose he had gone 20 meters in this direction, S1, but then he had gone, let's say 15 meters like this. My second one was like this. It's not 90 degrees anymore. It's some acute angle. This angle here is some acute angle, theta less than 90. But here, so 90 degrees. Suppose this is 30 degrees or something. Now, what we can say about the net displacement? We cannot, I have no idea exactly how much it is. But I can say one thing for sure, it is not 25. If you compare this triangle with this triangle, you can see that the net displacement here, definitely it is greater than 25 meters because this has got stretched. And at the same time, if I compare with my first diagram, I can also see that it is definitely less than 35. It must be some number in between. And what it is, now it depends on the value of theta. Okay, where obviously theta is some acute angle greater than 0 but less than 90. So if theta is between 0 and 90, we can see that the net displacement is between 25 and 35 in this case. So this type of analysis, this is called vector analysis. This is in fact called vector addition. So we will see that vector quantities are such that they have direction, which means that when we add them, we have to develop some new type of algebra. We cannot add them like scalar quantities are added. Like if I said the two distances covered were 20 meters and 15 meters, then it doesn't matter whether you are going in this diagram or the second diagram or the third. Every time if he's going like this through 20 meters and like this through 15 meters, the total distance covered by him would be 35 meters. But when we talk about displacement, because displacement is a vector quantity, how we add the two individual displacements S1 and S2 to get the net displacement, it depends on the angle between these two. It depends on the directions of the individual S1 and S2. And therefore, we say that displacement is a vector quantity, whereas we saw earlier today, electric current is a scalar quantity or resistance was a scalar quantity. Okay, so the first, you can well understand here why this is so important, because we have seen earlier today that the entire subject of physics is about physical phenomena, how physical quantities, which are quantities that can be measured, they affect each other through the mathematical modeling that we do. So if we want to understand the entire universe, we will definitely be dealing with a lot of physical quantities which are vectors, like displacement, force, momentum, velocity, electric field, magnetic field, and so many more. So that means we have to first understand how to do the algebra of these vector quantities, which have both magnitude and direction. Only then we can proceed further with our further understanding of physics, like when we study forces in Newton's law, or when we study, Coulombic force, electrostatics in the chapter of electrostatics, or when we study magnetism, so we are dealing with magnetic forces. Okay, so in all these further chapters going ahead, we will have to have some idea about vector analysis. So that is why the first topic that we'll be starting from next week onwards in physics will be something called vectors or vector analysis. Okay. And if you go through your module 1 in physics that you might have received the PDF of, you'll see that the first chapter in it is in fact vector analysis. So this is what we will be doing next week when we start our syllabus. Okay, today was just an introduction lecture. I'm repeating. Okay, nothing we've done today is any kind of systematic chapter or anything. It's just a general discussion on physics. Therefore, no homework for today also, right? But next week when we start, this is one of the topics which will be in your fundamental physics, which is vectors. Okay, so yeah, I will show that beta. You know, I will, to answer your question. Okay, I've missed out the question now. Yeah, Arya, to answer your question, there will be a systematic formula which we will learn by which we can calculate that net displacement given that angle. And that formula is called the triangle law of vector addition. And if you like, you can read ahead also, you'll get an idea of it. So we'll be coming to it very soon within the next week. Okay. So anyway, that's it for today's session, people. Hope you've enjoyed the lecture somewhat and enjoyed the discussion. Thanks for attending and wish you all the best. Yes, Rohan, I will be.
Thank you,
Okay.
sir.
Thank you, sir.
All the best.
Thank you, sir. Bye,
Thank
sir.
you, sir.
Thank you, sir.
Thank you,
Okay,
sir.
bye.
Thank you,
people.
sir. Bye, sir.
Bye, sir. Thank you, sir.
Video.
Thank you, sir. Bye.
Bye, sir. Thank you, sir.
Bye.
Thank you, sir.
So,
Yes.
so you are sending the recording video after the class, right?
Yes, Rohan, it will take like a few hours because I have to upload it on our channel and then I will send you the link of the channel. But
okay,
yes, I
sir.
will be sending by today evening. Okay. Both the
Yes.
recording as well as the whiteboard notes. Okay. Both the things I will be sending.
Okay. Thank you, sir. Bye, sir.
Okay. All the best. Bye, people.